is Javier Subils from Utrecht.
Okay, yeah, thanks for this opportunity to present my work in collaboration with David, who's here in the audience, also Vilke and two master students. And thanks for being here to attend it. Maybe one of the most intriguing features of gravity is how difficult it is to prove it beyond the classical level. So, you know, there's this theory, which is general relativity, that we know and we love. But, yeah, we expect it to break down at some point if curvature invariants become large. That would allow us to probe something beyond classical level. This happens at singularities. However, it seems that nature protects these singularities to be visible, and typically they appear behind horizons. This statement comes with the name of cosmic censorship. And it's kind of a natural question to ask whether there's any system where we can see curvature corrections, where curvature corrections become relevant by seeing that curvatures are growing. So there are some examples of this, which are violations of cosmic censorship. For example, if we consider collapse of matter in 4 dimensions, well, typically if we have enough matter, this will produce a black hole. If there's a small amount of matter, this dilutes, and there's a critical situation where a singularity is produced. However, this is kind of unsatisfactory because it's kind of a fine-tuned scenario. In higher dimensions, something more interesting can happen, which is that there are, you know, black holes can have a more interesting topology, and this could lead to an instability known as Gregory-Laflamme, in which case these black holes can pinch off, and when the pinch off happens, we also have large curvatures involved. However, in this case, as you can imagine, the region where this curvature correction would be relevant are kind of small, and also the energies involved there are also small. So again, it's kind of natural to ask whether there is any situation where we can produce large curvatures in an extended horizon, yeah, and also without any fine-tuned initial conditions. And that's kind of what I want to show today. So, okay, the contents of the talk are: first I will introduce the model, then we will explain the dynamical evolution that we consider, and finally, yeah, we'll see that curvatures will grow at the horizon. So this is the model. This is 5-dimensional Einstein-Dilaton gravity, and then, okay, I'm considering gravity plus a scalar, and then, okay, this potential that I'm including for the scalar will have some features. First of all, this has a maximum at the origin. This will allow for ADS solutions, and, okay, because of this, all the solutions I will present will have a holographic dual. And then this is kind of the UV of, there's a UV CFT which describes the high energy physics of the system. Then this will be formed by a source, this CFT, which in the bulk accounts for the scalar to having a mass. And then crucially, this potential will have a diverging behavior as phi grows, so this will go to minus infinity. Now, this is an important slide. Should we worry about the fact that the potential is diverging negatively as phi grows? Well, typically this could seem worrisome, but I want to argue that it's not, and it's actually a sensible thing to do. So first of all, should you worry about the fact that it's unbounded? Well, in ADS this is not necessarily a problem, and actually we are kind of familiar with the fact that we can have negative mass scalars in ADS, which, as long as they are above the BF bound, are not problematic. So, and this would also lead to an unboundedness from the point of view of the potential. Secondly, I want to state that generically one gets this kind of potentials in compactification of string theory. So if you take 10-dimensional string theory view and you compactify it in some compact manifold, in the effective lower dimensional theory you will get this kind of potentials. And actually, everything I'm showing today is motivated by a study we did many years ago, in which we had this kind of potentials in a lower dimensional compactified theory. But if you go to the uplifted theory, which in this case was in 11 dimensions, you can find a perfectly regular ground state. So even though that from the lower dimensional point of view, the theory may seem sick, if you don't like these kind of potentials, you can actually regularize or find regular solutions, regular ground states in, well, 11-dimensional supergravity in this case. Okay? And it's not the only example in which you find this kind of potentials.
Is there any restriction on gamma? Okay.
Yeah, so I should say that in my case, so I'm doing bottom up because, okay, this is our motivation, but of course this is difficult. There are many scalars in these setups. So I'm just, taking this potential that gathers the key features of the things I have in mind. So here, yeah, I will show this. So gamma is some number. I will play a little bit with it. So there's some range in which we have the same physics, but yeah, you can't take any gamma that you would like. We can discuss later if you want. But okay, this is kind of the motivation. I could be speaking for hours about this model that I love, and if you are interested, please ask me. But this is kind of the motivation, and okay, if you are worried about positivity theorems, also the fact that you have supersymmetry, well, makes you, and the fact that you can find these kind of regular ground states makes you confident that, yeah, energy will be bounded from below by these ground states. So, yeah, bear with me that this is a sensible thing to do, and this may be one of the most important slides of the talk. So, okay, let's take now these kind of potentials. What should we do? Well, first, to gain some intuition, we can study thermodynamics, and for that, you can construct black brane solutions. So then, this will be related in the gauge theory side to thermal states. And then the properties of thermal state are related to properties of these black brane solutions. For instance, you can construct the equation of state. I'm plotting here the energy as a function of temperature. And, as I was saying, for kind of a wide range of these gammas, you generically get the same. So the energy goes to 0 as the temperature goes to 0. Maybe this plot is not super illuminating, but we can also plot the ratio between pressure and energy, and then you see that they all start at high energies in 1/3, reflecting the fact that there's a CFT, and then they flow to some particular constant, which is determined by this exponential behavior of the potential. So now, okay, note that low temperature, low energy solutions are exploring deeper and deeper the potential. And actually what you see is that the smaller the black brane, if you want, the higher the curvature at the horizon. So the question we ask is that, is there any way to reach these highly curved black branes in a dynamical setup? So we want to start with some regular initial conditions that will evolve and explore this region. And then the answer is yes, and for that I consider boost invariant setup. So this is in a way inspired in what you see in high-ion collisions. So you have a pair of ion collisions, they collide, they produce quark-gluon plasma, and then this will expand and cool down. And this is kind of, in some regimes, well described by boost invariant setup. So you have your fluid here, then starts expanding and cooling down. So I want to put this theory in this setup, expecting that you will reach this cold regime where curvatures grow. And to do that, well, I use holography, so I will look for 5-dimensional metric, which is asymptotically ADS, asymptotically flat, but written in boost invariant coordinates. And then I will set up some initial conditions in a initial tau slice and let them evolve. And then what do we find? Well, we find what we expected. As the time goes on, what we see is the curvatures start growing at the horizon. So here I'm plotting the Ricci scalar as a function of time at the horizon for different choices of gamma, and then the Gressman scalar at the horizon for different choices of gamma as well. Now we can ask, is this sensitive to the initial condition? So actually you can vary the initial condition you started with, and as you expected, because this has been seen in holography before, so you expect that very soon the system hydrodynamizes. So after some initial time where the system is out of equilibrium, you reach this kind of attractor behavior, which you can check that it's well approximated by hydrodynamics. How am I doing with time? Sorry.
You have consumed 9 minutes.
9 minutes. Okay, fine. Yeah. So here what I'm doing is changing these initial conditions, and then I'm plotting the transverse pressure to a fluid and the longitudinal pressure to a fluid. And then you see, as I said, I'm fixing one particular value of gamma now, but it would be similar for other choices of gamma. And then, indeed, it relaxes to the hydrodynamic regime. This can be made more precise by considering, so you can, what I just described is what the solution is doing in the bulk and what we get. But you can actually, because you know the properties of the plasma, because we studied thermodynamics, you can actually solve the hydrodynamic equations for this plasma. And then you compare them. So you compare the microscopic evolution given by holography to the hydrodynamic evolution given by hydrodynamic evolution. And then you see that from the very early times, they kind of coincide. So here, one is sitting on top of the other, and then if you look at the difference, well, it's 10 to the minus 5, okay? This is interesting because it means that we can trust the hydrodynamic description, and actually, since, okay, these computations take a lot of time in a computer, but since hydrodynamic applies, we can say, okay, now that the fluid has hydrodynamized already, we can just take the hydrodynamic evolution and using fluid gravity correspondence, read off what the bulk is doing, and in particular read off what the curvature are doing at the horizon. And this is kind of what I'm showing in this plot. So here you have, again, the curvatures are a function of time. The solid line stands for those curvatures that are computed in the full hydrodynamic evolution, and the dashed line is the fluid, the one that is given by a fluid gravity approximation. And then you can match, eventually what happens to the geometry is ruled by the leading exponential, which you can kind of guess analytically, you can compute analytically, and we recover that, okay? And then you can compare what the fluid gravity approximation is giving you to what the hydrodynamic approximation is giving you in the region where you have both, and okay, you see that the error is small, it's 10 to the minus 2. So that's cool, and then we see that curvature are growing exponentially, meaning that at some point, we cannot trust the solution anymore, and we should include these curvature corrections. So in a way, we are proving high energy gravity, or if you want, quantum gravity. Well, so I will conclude. I have presented a way to generate dynamically these large curvatures in the bulk. The mechanism in a way is robust, because even though I work with this potential, it just relies on the fact that it's unbounded from below. This is a generic feature in compactification of string theory. And actually, I consider it an exponential, but if you were to consider polynomials that also are unbounded, this would also work. So in this sense, it's generic, and also it's simple in the sense that it's intuitive, right? So it relies on being able to cool down the system. I used here boost invariant expansion. You could wonder whether there's another way to cool down this plasma. That would be a great outlook or something to look at. And of course, now that it seems that this is working, maybe we could also consider some of this compactification of string theory that would mean including more scalars and see whether this can be found in a truly string theory setup. Thank you.
Javier? Hi.
Yeah.
So, what kind of initial conditions do you impose? It's a scalar, you perturb the scalar field, that's it, in a very localized way?
I guess you're asking about this. Well,
or the next plot, you have a plot where you have, for example, this one. So,
right. So here you need to impose all the UV expansions that are fixed by this, but then there's some freedom in the profile of indeed the scalar. And then also the B function, you know more than I do about these computations. In the metric, you have some freedom for the fields that you include. You can consider different profiles for those. Say that you take some cosine and then you start changing the phase or stuff like that. and then yeah, you get this. I don't know
And
if
this growth on the curvature occurs for any initial condition that you...
Well, I wouldn't say it's any, but for sure it's kind if you want, it's an open set around the initial condition, well, any of those, which is what you want to claim that it's.
And when you say that the curvature or the pullback of the curvature at the horizon is growing large,
Yes.
it's growing large everywhere or in a specific region of the
It's
horizon.
everywhere at the horizon. Yeah,
So it's not localized in the
it's
horizon?
not localized. But you still have the gauge theory directions. You have all of them.
So it's not
It's
something...
true that at the bulk, so the horizon is receding. Yeah, but still, for example, you have all of the transverse directions. The horizon is still there. I should also say that we study quasi-normal modes of this, because you could wonder maybe if you would excite the coordinates you are not allowing, whether this would like to be unstable in that sense, but apparently, we compare that to the relaxation time and it seems stable. Yeah, but it's going everywhere. I mean, it's not a strict, maybe I should say this, it's not a strict violation of cosmic censorship in the way people have in mind, because you never reach the singularity in finite time, but what is true is that, curvatures are growing, so no matter how small the Planck length is, you will eventually reach that region.
Okay, thank you.
Yes.
If you happen to add, say, a high curvature term, you may expect that will modify this.
Right, that's a very interesting question. So what would happen, imagine you would include some Gauss-Bonnet term, something like that. I don't expect that to be relevant at the beginning, because that's the region where curvature is small. But as you cool them, as this is cooling down, they would become relevant. And then you would see that in transport coefficients, for example. So if you believe that this plasma is describing, if this system is describing some sort of plasma, you would see that the properties of the plasma change, because you would see changes in the transport coefficients, for example, that you could measure. Okay.